The outdoor unit of an HVAC system has one primary job: rejecting massive amounts of heat from the building into the outside air. To verify that the unit is actually doing this effectively, technicians measure two field metrics at the machine: pressure and temperature. Comparing these two numbers produces a calculation known as subcooling. This calculation is the mathematical proof that the condenser is functioning. Many technicians attempt to evaluate system health by reading a pressure gauge and assuming the dial tells them the exact temperature of the refrigerant. It does not. Gauges only show physical pressure. By taking the extra step to calculate subcooling, you eliminate guesswork. You prove exactly what the refrigerant is doing inside the coil. Refrigerant inside the system exists in one of three conditions: saturated, superheated, or subcooled. Whenever refrigerant is actively changing states, it is saturated. Inside the condenser, saturation happens as hot vapor rejects heat and condenses into a liquid. Once 100% of that vapor is boiled off and turned into a liquid, the phase change is complete. Any additional heat the fan removes from that pure liquid cools it below its condensing point. That extra drop in temperature is subcooling. We calculate subcooling because it is the only way to prove that the vapor has successfully and completely condensed into a liquid before moving further down the line. Looking at this refrigeration cycle diagram, we can trace the exact path the refrigerant takes through the right half of the system. High-pressure, superheated vapor leaves the compressor and flows directly into the top loops of the condenser coil. As the vapor moves through the coil, the condenser fan removes heat until the refrigerant reaches its saturation point and condenses into a liquid. That completely subcooled liquid drops to the bottom of the coil, exits the unit, and travels down the liquid line toward the metering device. Because the entire goal of the condenser is to output pure liquid, this small liquid line is the only accurate location to measure subcooling. To gather the numbers for this calculation, you need a high-side manifold gauge, a temperature clamp, and a pressure-temperature chart. Remember, your manifold gauge reading only shows the physical pressure inside the system. It is not the actual saturation temperature of the refrigerant. This PT chart allows you to translate the pressure reading from your high-side gauge into its exact condensing saturation temperature. With that translation complete, you can use the subcooling formula. Take your condensing saturation temperature and subtract the physical liquid line temperature. This requires taking a reading with your temperature clamp. Secure the clamp strictly to the small copper liquid line leaving the condenser. Placing it anywhere else will invalidate the reading. If you skip the PT chart translation, you cannot calculate subcooling. The physical pressure on its own does not confirm if the refrigerant has successfully changed state. Let's apply this formula to a real-world R410A system. Step 1. Check your high-side gauge. For this unit, we pull a head pressure reading of 365 psig. Step 2. The PT chart converts 365 psig into a 111-degree saturation temperature. Step 3. The liquid line clamp reads 97 degrees. Subtracting the liquid line temperature from the saturation temperature, 111 minus 97, leaves exactly 14 degrees of subcooling. On a standard system, typical subcooling ranges from 8 to 15 degrees. Our result of 14 degrees means the condenser is operating within healthy parameters. If the subcooling calculates higher than 15 degrees, liquid is backing up inside the condenser. This points to an overcharged system, or a restriction in the metering device. If the subcooling falls below 8 degrees, the condenser is underfed. The vapor is struggling to condense, which is the primary indicator of a low refrigerant charge. Measuring subcooling gives you a verifiable window into the condenser. Instead of guessing based on gauge pressure, you calculate exactly how the refrigerant is behaving and diagnose the physical root of the problem.